Hello everyone, my name is Ambroise Moreau. I'm a PhD student at the University of Mons in Belgium, and today I will speak about our work about unsupervised depth prediction and how performances can be improved thanks to instance segmentation. To start this presentation, I will briefly introduce the context and our motivation. I will also give an overview of the related work in depth prediction, instance segmentation, and multitask learning. This will lead me to the description of our method, the experiments we did and the results, and finally I will conclude on this work and give some prospects of improvements. The first things we need to say about machines is that they need to be aware of depth to move in space and also to avoid obstacles. Then machines also need some knowledge about the objects so that they know what is around them and they are able to interact with objects. These two observations motivate us to build a system that is able to estimate depth and find instances at the same time. Depth prediction has already been successfully achieved thanks to convolutional neural networks. The first attempt was that of David Hagen and Rob Fergus. They proposed a common architecture shown on the left that can be trained to predict depth, surface normals, and semantic labels. The three tasks are trained separately, and the depth task is supervised through the minimization of an L2 norm between the prediction and the depth ground truth. The fact that depth labels are required to supervise the training is an inconvenience because such datasets are harder to record. So, in his work, Garg showed that it's possible to predict depth by teaching a model to perform view synthesis as explained in this image. The left image of a stereo pair is fed to a CNN that predicts the depth. Then, from the depth, the right image, and the camera motion between the pair, it's possible to synthesize the left view. In that case, learning is supervised through the minimization of the photometric error between the original left image and the synthesized one. Following a similar approach, Godard and others have imposed a left-right depth consistency to avoid degeneracy, and Zhu and others proposed to solve the post-estimation problem to be able to use monocular sequences instead of stereo pairs. CNN are also able to find objects in images. There are all the RCNN models that work in 3 steps. First, they generate regions of interest, then they extract features in these regions, and then finally they classify the objects. In addition, mask RCNN creates instance masks for the detected objects. In parallel to the region proposal methods, there are also the proposal-free methods that rely on pixel embeddings and work in 2 steps. First, they compute the pixels embeddings, for instance, the x and y offsets between the pixels coordinates and the center rate of the object, as shown in this image. And then they cluster the embeddings with an algorithm such as optics. Finally, it's possible to train a model to solve different tasks at the same time. This is the case in the work of Kendall and others who propose a model that solves semantic segmentation, instance segmentation, and supervised depth prediction. To solve the 3 tasks at once and get optimal results, they balance the losses with homoscedastic uncertainty, which is the task-dependent uncertainty. Liu and others have also trained an architecture known as M10 to solve more than one task. Their approach uses a shared network and then task-specific attention modules that generate task-specific features. They also propose the difference rating technique known as dynamic weight average. So far, we have shown that it's possible to estimate depth, find instances of certain objects, and solve several tasks at once. Nevertheless, None of the multitask approach solves unsupervised depth prediction, so in this work, our goal was to propose a multitask architecture that solves unsupervised molecular depth estimation and instance segmentation. To solve depth estimation, we rely on monodepth2, which has two separate networks. The depth network, shown here, that predicts depth from an image IT, and the pose network that estimates the camera motion between images T and T prime. The model uses the view synthesis principle to recover the depth information. There are two main differences between monodepth2 and our model. First, we are not using a separate pose encoder, and second, we feed 3 images to the network at once. For the instance part, we need a feed-forward network that computes spatial embeddings. The principle is explained on that image. So the network takes an image as input and predicts the x and y offsets. Learning is supervised through the minimization of the L2 loss between the ground truth embeddings and the predictions. Finally, the multitask aspect of our model is addressed with the attention modules of N10, and this figure shows the final architecture. The blue part represents the shared part of the network. The first line of orange blocks represents the instance-specific features. The second line is the pose-specific features, and for this part we are not using the attention decoder, but we use the pose decoder of monodepth2. Finally, the third line represents the depth-specific features. The output of the depth attention decoders and the pose decoder are combined in a multiscale photometric loss, and the output of the instance-specific features is used to compute the L2 loss. The two functions are combined to form a multitask loss that implements equal weighting, homoscedastic weighting, or DWA. During our experiments, we trained our models on Kitty and cityscapes with 39,810 training and 4,424 validation triplets of images. We have 697 test images for Kitty and 2,000 test images for cityscapes. For the instance segmentation part, none of the two datasets provide instance annotations for the sequences, so we generated the ground truth with mask RCNN trained on cityscape to find 8 different classes. In all our experiments, the model is trained for 20 epochs. We trained different versions of our architecture, one version that solves instance segmentation alone while using the task-specific modules, one version that solves depth and pose prediction, the multitask version with equal weighting, the multitask version with homoscedastic weighting, and the multitask version with DWA. The results are shown here in this table that reports the values of the 7 metrics that are commonly used to evaluate depth, and monodepth2 is trained on Kitty and cityscapes. From these numbers, we can see that the single task configuration of our model gives poor results when trained on cityscapes. This is partly explained in this example in which 2 cars are moving at the same speed as the camera. We can see that these 2 objects are too challenging for monodepth2 and our single task configuration, but it seems that when coupled with instance segmentation, the model manages to estimate depth values. Then the best results on Kitty are obtained with the multitask configuration and DWA, and the best results on cityscapes are obtained with the same configuration. Regarding the instance segmentation evaluation, our model does not recover semantic information, so we cannot report per class metrics. Instead, we report the mean squared error as in the work of Senner and others. From the number, it appears that the single task configuration trained on cityscapes gives the best results on both datasets, but the multitask configuration yields close values on cityscapes, with homoscedastic weighting. So it seems that depth and pose estimations do not help instance segmentation as much as solving instance segmentation helps depth predictions. Finally, the embeddings computed by the models can be used with optics to recover the final segmentation map as shown here in this example. To conclude on this work, we proposed a multitask architecture that solves unsupervised depth and pose estimation, as well as instance segmentation. Solving instance segmentation at the same time seems to help the model in challenging situations, such as when cars are moving at the same speed as the camera. But on the contrary, instance segmentation does not benefit from the other two tasks. In the future, we will probably add semantic segmentation to the list of tasks. We also want to analyze the attention masks computed by the soft attention modules for each task. And finally, we want to train on datasets with more accurate instance ground truth sequences such as in MUTs. Thank you for your attention.